Okay, so our second speaker of the morning session is Mohammed ABOUZAID from Stanford. So he's going to talk about global charts for moduli spaces of pseudo holomorphic curves.
Okay, thank you, Gongbo. It's a pleasure to be here. It's a little bit embarrassing to be speaking at a conference on geometric analysis. Somehow, when I was a graduate student studying symplectic topology, I was asked by my advisor, Paul Seidel, to read some papers. I mean, a lot of papers. I'm not going to put all of them down. Since this is Tien's birthday, I will put the papers of Tien that I was asked to read. I was asked to read this paper, Mathematical Theory of Quantum Cohomology. And this paper, maybe you can't see, but the main result is stated over there. And it says something like, if you have a symplectic manifold and there is this condition of semi-positivity here, which says that the symplectic form, that there are not any curves of negative index. This word index appeared in the previous talk. Then we can define some invariants, quantum cohomology invariant, Gromov-Witten invariants, now they're mostly called. And then there's this composition law that holds, oh yes, you can point to this, okay. Right, there's this composition law, and this composition law is some kind of associativity statement. It says when the curve breaks, that the count is basically the product of what you get for the two components. Anyway, this paper I understood, at least I think I understood. Its main idea was that you basically would produce some manifolds, and you would count in the number of points that these manifolds have, and then you would prove invariance under cobordism. And then at some point I was asked to read more papers, oops, how to do the next page?
Yes, click.
Oh, there we go, click. Okay, like this paper about virtual moduli cycles and Gromov-Witten invariant for general symplectic manifolds. And it starts, this is from the very beginning, I cut it off, but it starts by saying, well, it's well known that if you take a Banach manifold and you have a Fredholm bundle, then there's an Euler class, and then we could, that somehow the work of the previous paper kind of would fit within this picture more or less. But then its use is very limited. So we have to do something more complicated, and I never managed to understand the more complicated thing. And somehow I'm not an analyst. That was my excuse. So, and there's of course other approaches that's been developed. In fact, I don't have the citation here, but in this paper it says that while they were writing this, Fukaya and Ono were developing their own approach. Which was more finite dimensional. Okay, so that's more like my thing. But Fukaya and Ono's approach was also kind of very hard, a bit hard, and involves like finite dimensional, small finite. So the trade-off has always been you either kind of go to infinite dimensions and you work with these very complicated generalizations of Banach manifolds and Fredholm bundles, or you try to work with small finite dimensional pieces, and then you have very small finite dimensional manifolds, finite group actions, and maps between them. But then you have these small charts and you try to glue things together. Okay, this has always been the difficulty in the subject. So the title of this talk is something about global charts. And if you hear this word, you should find it a little bit suspicious, because one of the things that happens in the story is there's always a group floating around. And you cannot expect, so there's a group floating around, and the best you can hope for often is to have an orbifold. Okay? And an orbifold is modeled after the quotient of a manifold by a finite group action, but it's pretty easy to get examples already of Riemann surface of orbifolds in dimension 2, where you can kind of locally have such a presentation, but you don't have such a global presentation. You cannot present them as just some Riemann surface modulo of finite group. So this word global means something slightly different for us. It means that we, at least from my perspective, we try to find something intermediate between these two levels of difficulty, which is that we are going to look at finite dimensional manifolds with actions of compactly groups. Okay? So let me say more precisely. So this is kind of, to me, the dream, the most reasonable dream. Which again, for somebody who doesn't do geometric analysis, the dream is to remove infinite dimensions from the picture. So what we want to do is we want to present M, and here M, what I mean by that is the moduli space of pseudo-holomorphic curves with target some symplectic manifold in a fixed homology class. Okay? You make the symplectic manifold closed just so that you avoid some issues at infinity. There is always a story that, there's always some condition you can put at infinity to get rid of the problem. So originally, the original work that I did with my two co-authors, Mark McLean and Ivan Smith, was in genus 0. But since then, the story has been generalized to higher genus. So we're kind of both by us and by another group of postdocs, Swaminathan and Hershey and Swaminathan. Anyway, so that's what I mean by M. Some moduli space of curves. You fix the homology class that gives you compactness. And then there's some target symplectic manifold I'm not writing about. Okay, so what you want to do is you want to present it as S inverse of 0 modulo G. Okay, so what does that mean? Well, G is some compact Lie group. And as I was saying before, that's the best you can hope for. Because in general, you're expecting to get an orbifold, and you get very general orbifold from this story. And now, well, this S means somehow there's some function or some section. It's really going to be a section. So the section is defined on some T, which is some smooth G manifold. It's not going to be closed. I mean, of course, you can try to artificially make a closed manifold, but the natural construction produces something open. Now, that's surprising. That's at first kind of annoying, because the M that you produce, because I started by fixing a homology class, satisfies some compactness property. That's why we can count it. Okay, but that's kind of not unreasonable. If you can embed any closed manifold inside Euclidean space or something like that. So there's going to be an ambient space where everything is defined. That would somehow a space of let's say smooth manifolds, smooth maps, but it's not really. It's just more general than pseudo-homomorphic maps. And that's T, space somehow. Imagine it's like the space of some finite dimensional subspace of the space of all maps. And then there is some equation that you're going to impose. And instead of writing it as a equation is mapped to something, you write it just like in this paper of Chen that I was citing, Chen Li, that I was citing. You write it as you have a vector bundle over your T, and it doesn't have to be, now we're out, we don't have to say Fredholm, it's just a finite dimensional vector bundle with a G action. Okay? And then there is a section S. And when you have this section, you can just, of course, take the 0 locus. And what I didn't write is implicitly what's happening here is we assume that the 0 locus is compact, because that's what's going to give us the fact that M is compact. And then we take this modulo G, and that will give us the modulo space. Okay? This is what we want. I mean, or at least this is what somebody who doesn't know how to do geometric analysis would like to, how they would like to package the outcome of some geometric analysis, which is studying the structure of the moduli space of pseudo-holomorphic curve. You have to do analysis somewhere. But the idea is that once you've done that analysis, you'd like to package it in some box, and this is a very convenient box, and even a topologist who doesn't know anything about Cauchy-Riemann operators can kind of then go on and use this. Now, there's something that is kind of implicit in this dream that I didn't quite explicitly say. So, for example, so the action of G on T, okay, it's it would be really quite bad if this action had stabilizers that were non-trivial, that were higher dimensional subgroups, okay? Because that would introduce really bad singularities. So implicitly in this story, we're kind of assuming that G acts on T semi-freely. Okay? So finite, all stabilizers are finite. And again, we cannot expect something better than that, because the moduli space is supposed to be an orbifold. As an orbifold, there's some points, or even in the best of all situations, the points would have neighborhoods that are modeled after Rn modulo finite group action. That finite group should be reflected in the story here. And the other thing that I'm not saying is that that finite group should be the stabilizer of a point in S inverse of G, in S inverse of 0 under the group G. Okay. So this should be a presentation of M not just as a topological space, but as a Orbi space. I've been saying orbifold, but for the whole reason that there are some difficulties is that in general we cannot even ensure that M is a smooth manifold. Okay, so if you have this picture, you kind of start seeing some non-trivial abstractions to even making M into a manifold, into an orbifold, because sometimes if you have a G manifold and if you have a two map between G manifolds, you cannot achieve transversality within the space of equivariant maps. So and that is just ends up being some representation theoretic question involving the tangent space of T as a representation of the stabilizer group, and the fiber V as a representation of the stabilizer group. If those two things kind of don't share the same irreducible components, and there's going to be no maps between them, you can't do transversality. So in some sense, at least from a very abstract kind of topological point of view, this is the best you can hope for. So I was told 30 minutes is not a long time, and I can, good. Now the idea for building something like this goes back to Siebert. Siebert had a paper where he basically wrote down some comparison between algebraic and symplectic Gromov-Witten invariants. And the starting point of what he proposed to do is to put in some extra structure. Now, normally, when we do Gromov-Witten theory, we say you have a symplectic manifold, like I'm calling it X here. We just, well, has a symplectic form. That's what we're trying to study. We equip it with the additional structure of a compatible, almost complex structure. That's what allows us to study pseudo-holomorphic curves. Then you have a whole story of showing that things are independent of the choice of J, but okay, that's the standard thing that even in the semi-positive case, you have to do this. Now, what you could do is you could pick some extra data. And the extra data that Siebert was working in the case where X was projective variety for him. So for him, you just pick a polarization. Okay, but for us, we want to work with arbitrary symplectic manifolds, so we want to pick an additional kind of the data of a complex line bundle. More precisely, we want it to be a Hermitian line bundle, so we have some kind of metric on it. Okay, so how can this help? Well, this can help us because somehow we're going to choose some extra data on this that's associated to this line bundle, and the space of data will be quite large, but finite dimensional, and then a group will act on it. Okay? And then that will be the building block of this space T that I'm interested in. So what kind of data are we going to look at? Well, just consider some Riemann surface sigma mapping to X, okay? And look at the pullback of L. Okay? This is now a complex line bundle on sigma. Sigma is a Riemann surface. I said this is Hermitian, so it has a metric. Okay? So by some correspondence whose name I forget, you know that there is a unique holomorphic structure floating around. So I can now think of U star L as now a holomorphic line bundle on sigma. Okay? And as such, I can look at holomorphic sections on it. Okay? So I wrote the wrong thing here. I said bases of U star L. This is not what I mean. Bases of H0 of U star L, of the space of holomorphic sections. Now, if the line bundle is arbitrary, this is a stupid thing to do. Like if it's negative, then there is no sections. Okay? But the whole point is to pick this line bundle so that this H upper 0, which I didn't write over there, this pullback, the space of sections is in fact reflects the geometry of the situation, i.e. we want to make sure that U upper star of L is in fact ample, or maybe very ample, make life even better. I mean, I'm assuming sigma is genus 0 for the beginning, so that's not too big a difference. Now, how do we achieve that? How do we find such a line bundle? There is the easy case and the hard case. The easy case is the case where you don't need any of this machinery, where you just assume that the symplectic form on our target is lies in integral cohomology. So it's in H2 with Z coefficient. So the symplectic form is already the curvature of a line bundle. Okay? And then there is almost nothing to do. You just take that line bundle and work with it. The hard case is, well, what we call the irrational case. Symplectic form is not rational. But then what you can do is you can approximate it. It turns out, I mean, this is an easy thing to say. You approximate it. In this world of Gromov-Witten theory, that's fine. You say, well, I'm looking at, you first fix the class of sigma, okay? Some homology class, and then based on that homology class, you know that you can kind of perturb the symplectic form a tiny little bit so that this class remains positive with respect to it, and then perturbation can be made rational, then you take a large multiple, and there you go, you have your integral form. Okay? So that's where L comes from, and then once you have that, you know that looking at H0 of L is a reasonable thing to look at. The fact that the metric was Hermitian, I didn't say this, means that not only do we have all bases, we can look at unitary bases. So what have we done now? Well, we have a space, which is basically just the space of bases of the space of sections of this line bundle. It has an action of a unitary group. If I take the quotient, you know, I get the moduli space. Okay? That's not what I want, because the space of bases will be basically as singular as the moduli space itself. Well, maybe we will undo some orbifolding problem, but if there is some lack of transversality in the definition of the moduli space, that hasn't helped us very much. Okay? So we need some additional step. What we want to do is so kind of embed this inside a larger dimensional space where we see other equations, not just this, you know, the whole pseudo-holomorphic equation, but some perturbation of it. Now, the problem is to write down another equation, you need a more concrete model, or it's useful to have a more concrete model of the domains than just saying, well, I just have some abstract Riemann surface mapping. Okay? And this is what this is good for. So that's what the Kodaira embedding theorem tells us. It tells us that if you have this basis, then you now have a map from sigma to projective space. Just evaluate. You know, you take the basis and you just evaluate it at every point. This projective space is, of course, like fixed projective space with, you know, with fixed coordinates in some sense. And you can then identify this action of the unitary group on the space of bases of H upper 0 with the standard action on CPD, which of course has this stabilizer S1 that fixes everything. You can either include it as part of include some extra data as part of it, or you can just take the quotient and work with the projective unitary group. So why is this better? Okay, this is better because now I can say, instead of my domain being some abstract curve, I'm just going to look at curves that have a map to projective space. Okay? There is a moduli space of such. It can be given coordinates. It's a very concrete type of object. Okay? You know, curves of degree, in fact, curves of degree D in projective space. Of course, they can degenerate, but we can understand completely their degeneration. So now I'm going to state the theorem. It's still not going to be completely clear. You know, all the details are not in, but hopefully I can kind of flesh it out. So the statement, and this is, I think, from around 21 is when we posted the paper. So it says, look at the moduli space of, you know, genus 0 curves in CPD of degree D. Okay. I don't want to look at all of it. I want to look at an open subset, which we call f of D. Now I can tell you exactly what this open subset is, because again, we're working in genus 0. This open subset consists of curves which are not contained, whose image is not contained in any lower dimensional linear subspace of CPD. It turns out imposing this condition makes f of D, it kind of gets rid of any orbifold point. So f of D is in fact not just an open subset, it is a smooth manifold. Now this is an orbifold, okay? So this is smooth manifold. And now it's pretty clear that this space, oh, I messed up there. The space has an action, you know, if you act on CPD by some automorphism, then you will, in fact, you will preserve the subset. So this has an action of the unitary group on D+1 element. Okay. Now, how do we use this? We're going to use this FD as the parameter space of our domains. Okay. So precisely, so not so precisely, it's still vague, but if you choose a representation, this should be UD plus 1, not UD. If you do choose a representation of this unitary group on D+1 the matrices, D+1 by D+1 unitary matrices, and actually a little bit more, you have to choose a representation, and then you have to choose a family of inhomogeneous terms for the Cauchy-Riemann equation that depends on this representation. Okay, And if you choose it large enough, then what you can produce is a manifold, which we call T of D, with an action of UD plus 1. This manifold projects to our f of D. What it really means is an element of this manifold consists of a curve in here, okay, which means a curve mapping to projective space. You can almost think of it as embedded, but that would require slightly different choices. But you can do that if you want. You can almost think of it as embedded in projective space. It consists of a curve in here, an element of this representation that I didn't name, so that, and a map to your target symplectic manifold X, also didn't write, so that this curve that you picked solves the equation that is determined by the element of the representation that I didn't name. Okay. Anyway, so we have this TD, and then you have some vector bundle, and then achieving what we want. This vector bundle has a section S, so that if I look at this section S and I take the quotient by the unitary group, I get exactly the moduli space of curves that I wanted. Okay, so that's our statement. So in this statement, there is a class beta that is fixed. I made the statement with 0, which is number zero marked points. In fact, there is a generalization of this, that's easy to do, where you have arbitrary number of marked points. Okay. And as I said at the beginning, you can also do this with higher genus if you want. Okay. So so that's the statement. Why did we want this statement? Well, if I go back to the beginning, which I don't know if I can do. Oh, yes, I can do. Okay. There was this remark. Well, again, just very beginning in the introduction, this paper of Li and Tian says it's well known, and if you have an orientable Fredholm bundle, there is an Euler class. Okay. And I would say it's even more well known that if you have an orientable vector bundle over a manifold, there is an Euler class. You don't even need finite dimensions. Now, what's interesting is that you can do these things equivariantly. So in our setting, the goal in these stories is always to produce some virtual fundamental class that's associated to the moduli space. And one question that somebody recently would have, probably more algebraically minded person should have for me is, okay, well, you produce this thing, how do you get the invariant out of this? And the answer is, there is some machine that says, if you have a G manifold and you have a G vector bundle on it, then that G vector bundle has an associated Euler class. That's an interesting statement, because where does the section enter? Okay, the section actually enters precisely because of the fact that our T is not compact. Okay, so if you have this Euler class, what are you going to pair it with in order to get a number? You need a fundamental class. So it turns out this section ensures that this Euler class actually lives in some kind of compactly supported cohomology, so that then you can produce your virtual fundamental class that is compactly supported rather than living in some non-compact thing. So that's just what this is. But now what we really wanted to do is somehow generalize this, and I don't have a slide about this. But the people who kind of again study manifold, finite dimensional manifolds for a living, and who think about other cohomology theory, they can tell you quite quickly that if you have a setting like this, not only do you have an Euler class in ordinary cohomology, but assuming that this vector bundle, let's say, is complex, it has a kind of a stable complex structure. I'm not saying holomorphic, just kind of, as a smooth vector bundle has some kind of complex structure, and this T as a smooth thing has a complex structure. Well, relative D, which means if you took T mod U, mod the unitary group, that is complex. Then your Euler class, you have now an Euler class in other cohomology theories, such as, for example, K theory. So the advantage, at least one advantage of working in finite dimensions and working with these global charts, is that the machine for producing invariant, enumerative, or just we call them enumerative, but I would say kind of fundamental classes, or Euler classes, because ultimately that's what it comes down to. Euler classes out of compact Lie groups acting on smooth manifolds already exist, and has existed since the time of Atiyah. Atiyah has a paper on transverse K theory from 1977, where they basically kind of extend some of the Atiyah Singer work, which somehow doesn't exactly apply to this setting, and which produces basically fundamental classes in equivariant K-theory. And once you produce fundamental class in equivariant K-theory, you can then project to ordinary K-theory. And there's, of course, other versions which are more elaborate and sophisticated and abstract, but including, in some sense, a fundamental class in some version of complex coordinates, some version of equivariant complex coordinates. So, the outcome, therefore, of this kind of introducing this formalism is that, not only can we kind of realize the existence of virtual fundamental classes that were known before, using kind of what I think is just a kind of a simpler geometric package, but in addition, we can also generalize to other cohomology theory beside ordinary cohomology. Okay, so I don't have much more to say on this subject, so I think I will stop, even though it's 5 minutes early, and I will wish happy birthday to Gangqin. Thank you.
Do we have questions for the speaker?
So when you go from one line bundle to another,
yes.
How do you go?
That's a good question. So the simplest way to go is to just realize that the notion of ampleness is not restricted to line bundles. You can talk about vector bundles that are ample, which means you can just take the direct sum. Okay. So I said something about, you think of your curves as being embedded in projective space or mapping to projective space. You have two line bundles. What you can just do is you can say take the product of two projective spaces and look at some subset of the space of curves in that product, and that basically does the comparison for you. There's other ways to go, but that's, I think, the simplest way.
And if somebody is algebraically minded and say, can your approach be done in an algebraic way? I mean, which step is the hardest step?
So that's a very interesting question. So the step that is the hardest is producing the section. So it turns out that in our setting, this T is a holomorphic manifold, is a kind of a holomorphic, complex manifold. This V, you can arrange for it to be a holomorphic vector bundle, but the section which defines the moduli space is not. Okay, so we worked very hard to do this.
So even if everything is projective right to the section?
Yeah, because basically it has some kind of pairing in it. It uses some kind of pairing. Somehow the unitary group is very close to being some object of complex geometry, but it's not a complex manifold. So that's basically what it is. And I mean, somehow, again, the reason that T is a complex manifold and V is a complex vector manifold is because we worked hard to try to get as close as possible, but we didn't get close enough. So right now, I don't know an approach, a straightforward approach to the comparison.
Other questions?
I think there is a case like homogeneous that you have to perturb constant maps.
Yes.
Do you have any idea how to generalize it to that story?
Yeah. So it is done. So we have generalized it to that story, and the answer is a little bit cheeky. I mean, basically, like you have to start with the knowledge that there is a moduli space of higher genus curves. Okay, and on that moduli space of abstract, and on that moduli space, you pick an ample line bundle, basically. And then you use that ample line bundle, and then you couple that ample line bundle with this line bundle L that I introduced, that comes from the symplectic manifold, and you tensor them together. So instead of just this L here, there is L and then some kind of canonical bundle. Actually, you don't have to say there is. You can just use the canonical bundle itself, because that will take care of everything. So you use L tensor K in all constructions.
So I guess understand that you choose the line bundle. I guess you don't need to be if a target manifold is algebraic, you can choose a holomorphic line bundle. In general, you just choose a complex Commission bundle, and which is quite positive. So you pull back to a Riemann surface by map and look at this orthogonal basis of H0. So that's how you enlarge your space, right?
Yes.
Yeah. Okay. So then you try to, in the end, try to use a unitary group to quotient out that to get the original moduli space. So is there some issue when this Riemann surface? I guess you need to do this on a stable sigma. So sigma may have some singularities, right? So
Yes.
So you need to incorporate that here.
Yes.
So when this degeneracy the line bundle, is there some issue about this line bundle near the double points? How you
So-
choose the section there?
Yeah, so in some sense, once you, so basically the most naive answer works, which means if you have a nodal Riemann surface, you just think of sections of the line bundle over this nodal Riemann surface as just two sections which agree at the point which is being glued, which of course makes sense because you have a line bundle on your symplectic manifold, okay? And now you have this nodal Riemann surface mapping to your symplectic manifold. So if you have a nodal point, it has two branches, the points that lie in the two branches, they map to the same point in the target. So when you pull back, the fiber at the 2 points is canonically identified. You have no ambiguity there. And then you just say, I'm going to pick a section on the two sides. My space of sections consists of sections on the two sides which agree at this point. And this gives you the correct dimension formula. Basically, what you want to make sure is that when the domain degenerates, the space of sections of this line bundle still has the same rank. And this ensures it. This ensures that it doesn't change.
So on the Riemann surface, you first kind of fix the kind of metric on the universal moduli space, universal moduli curve. Because near the nodal curve, it's I guess if you use hyperbolic metric, that's different. I guess here you just use the kind of fixed metric with how do I say? So it's a smooth metric on each pieces, which agree on the node, right?
On the node. So if you take the point of view of I'm going to start with the abstract moduli space of curves and then show that that is the same as this construction, then yes, at some point you have to do this comparison. But actually, you can cheat. What I mean by you can cheat is you can reverse the entire procedure and just say, I'm never going to look at abstract curves. I'm only going to look at curves that already have a mapping projective space because I have a bijective correspondence between curves in projective space and abstract curves together with line bundle of degree D and a choice of basis of H0 of this line bundle, which means you can start on the kind of moduli curves mapping to projective space side, and on that side you can just say, well, algebraic geometry tells me that the moduli space of curves in projective space is a smooth projective variety of degree D. But you are right. If you don't want to use this algebraic geometric input, then you have to make some choices about about metrics on Riemann surface, abstract Riemann surfaces, and so on and so forth.
Okay, sure. Thank you.
I was going to ask one question, but then I heard your answer to the other question, and I have now another question. But
okay.
So you said that TD is a complex manifold?
Yeah.
Is that correct? I mean, but you're looking at J-holomorphic maps?
No, in the case where the target is a projective variety, is a complex manifold, then TD is
Okay, but now in the general case, so presumably there's some kind of issue of gluing where you have like nodal curves, and then as I recall from looking at the preprint, there's like some issue of smoothing there, right?
Okay, so so I said TD is smooth. Okay, so the question is, how is TD smooth? So it turns out, I kind of like this approach because it kind of separates the issues. So I said that this TD has a projection to FD. Okay, so in fact, it turns out that this is some kind of submersion. Okay? When you start at the beginning, you want to use a minimal amount of gluing theory. What you know is this is a this is a projection map whose fibers are smooth manifolds. And if you go from fiber to fiber, those smooth manifolds can be, as basically, I want to say diffeomorphic to each other. That's not completely true, but you can ensure this actually at the near a broken curve. So this is the usual statement that says, if you fix a gluing parameter, then gluing is smooth. And then there is the question of what about smoothness in the transverse direction to gluing? Okay. So that we just solve abstractly. So we just basically prove if you have a topological manifold with some kind of topological submersion to a smooth manifold, and if the fibers are smooth manifolds and the smooth structures on those fibers varies continuously, then up to stabilizing, which means making this vector bundle larger, because we already have vector bundles anyway. Okay? There is a smooth structure, which is unique, up to, if you stabilize further, you can get a cobordism between them, okay? Concordance between them. Okay? But this is not something we invented. This is something very old from the 1970s on basically the problem of how do you smooth topological manifolds. I am actually working with Mohan Swaminathan on making this more explicit and removing the stabilization process from it. I actually think this can be done kind of just by hand, using the kind of things that we teach our graduate students when we teach them about Ehresmann's theorem. Okay? And I think that kind of machine can be used to actually produce kind of a contractible choice of smoothies given this data. Your base is smooth, your fiber is smooth. How many choices could there possibly be?
So my question actually is,
yes,
does this smoothing theory work for manifolds with corners?
So the answer is yes. You can find much written about it in this paper of Guangbo and Guangbo Xu and Xiaoyun Bai. Okay, yeah. So the answer is yes, and the reason basically they implemented this strategy for Hamiltonian Floer theory. And in Hamiltonian Floer theory, you have a differential, and you want to prove d squared equals 0, which means you're already going to encounter manifolds with boundaries and corners. And so they did this. Yeah, there's another. My former student Simon Reshikov also did something, but he did it by trick, and they just did it directly. That's it.
Any other questions? Okay. So if no, let's thank Mohammed again. So we'll resume at 11:30. Yeah, 11:30.